eigenvalue and eigenvectors. Let A be n times n matrix. Be careful, it's a square matrix. 2 times 2, 3 times 3, and keep going. And let the scalar lambda or lambda. This is like Greek symbol, okay? Some people they call it lambda, some people they call it lambda, okay? Is called eigenvalue of A. How are we going to find this eigenvalue? If there is a non-zero vector x such that here's the important condition. So now, this one is called lambda if there is a vector such that the matrix A times the vector equal the lambda, this is the variable lambda, or scalar, not the variable, times the vector. That means these two are equal sides. Such vector, we call it eigenvector. So for each eigenvalue, that means we have eigenvector. Eigenvector of A, of the matrix A, which is n times n, corresponding to the lambda. We'll check that. Before we go in here, I did some notes for you. AX, this is really important. AX equal lambda x. Exactly the same condition. Now, if you move the lambda x to this side, it's going to be AX minus lambda x equals 0. Take the x as a common, so it's going to be A minus lambda equals 0. Now, A is a matrix, square matrix, n times n. The lambda is what? Check here. The lambda is what? Is a scalar, okay? That means I can't say A minus scalar, because A is a matrix, lambda is a scalar. So what I'm going to do, I'm going to multiply this scalar by the identity matrix. So I can convert this scalar to a matrix, and I can say A minus a lambda times identity matrix. Now it's okay. This is going to be work. We're going to use this one a lot. With the vector equals 0. Okay. I'm going to show you how to find the lambda. There is a note on the slides. We're going to take the determinant for this one. Okay. We're going to start with n times n matrix. Then next section 4.2, we're gonna learn how to find the determinant for n times n matrix, but 3 times 3, 4 times 4, 5 times 5. Okay. Let's go back here. Let A be n times n matrix, and let lambda be the eigenvalue of A, the collection. Okay. Now I'm going to take all the eigenvectors, because you remember, for each eigenvalue, there is eigenvector. I'm going to put all the eigenvectors together with the 0 vector to make a new space called eigenspace. Okay? That means we're just going to collect all the eigenvectors in one space with the 0. So we're going to get eigenspace and denoted by like eigenspace for if lambda equal 1. That means the eigenspace for lambda 1, like let's say equal certain vectors. Okay. Perfect. It's like the span. We're gonna check that when we found the vector, we can call the span to this vector. Okay. We're gonna check that in an example. Yes. So now we're gonna check. We're gonna give you only the matrix, and we need to find the eigenvalue and eigenvector. So we're gonna use exactly the same thing, which is AX minus equal lambda x. Now, as always, we're gonna use that, but instead of using that, we have another. Remember the note. It says A minus lambda with in with the x equals 0. You can use this one. This is the eigenvector. You're going to find it. I'm going to just take the determinant here because this is a vector. I'm going to take the determinant here to find the eigenvalue. So I'm going to say it's the determinant for a minus lambda I n equals 0. Okay. Now let's plug in. Determinant is going to be 4. A, which is the matrix A, 3, 1, 1, 3, minus lambda times I, which is lambda 0, 0, lambda, okay? And everything equal to 0. I'm multiplying lambda with the matrix, the identity matrix, which is 1, 0, 0, 1 times lambda. So lambda is going to be 0, 0, lambda, okay? Now, this one minus this one. That means the determinant for three minus lambda, and here is going to be 1, because 1 minus 0, and here is going to be 1, and here is going to be 3 minus lambda. And everything is going to be equal to the 0. Now, to find the determinant for this matrix, we're going to multiply this one minus these two numbers. All right? Remember, when to find the determinant for 2 times 2 matrix, this one times this one minus 1 times 1. This is the inverse. We need to find the determinant for any matrix. You're going to multiply the diagonal minus the other. What do I call this one? I forgot it. This part times this one, okay? Like cross, when you find the determinant for 2 times 2 matrix, not the inverse, when you divide 1 by the adjacent, right? AG, ADJ. So the determinant is going to be 3 minus lambda times 3 minus lambda minus 1 times 1 equals 0. Now it's going to be 9 minus 3 lambda minus 3 lambda minus 1 is going to be equal to 0. I forgot the lambda square. Plus lambda square minus 1 is going to be 0. Now I'm just going to rewrite this one again and combine the like terms. So it's going to be lambda square minus 6 lambda. 9 minus 1 is going to be plus 8 is going to be 0. Now I need to factor this one. So it's going to be lambda minus 3 minus, let's do it 4, and lambda minus 2 is going to be 0. That's mean lambda is going to be equal 4, and lambda is going to be equal 2. So this is the eigenvalue. Now we need to find the eigenvector. I have 2 lambda, so I'm going to start plugging this one here. So this one is now the main matrix. I'm going to focus here. To find the eigenvector, it's easier to plug in and go back to the beginning. No, here's the matrix. So I'm going to plug in 4 here. Then I'm going to go back and plug in 2 instead of the lambda, okay? So when lambda equal 4, this is the first one. When lambda equal 4, I'm going to plug in 4. go back here and I'm plugging 4 here instead of the lambda without the determinant, because I need just to use this matrix here. So this one is going to be 3 minus 4. And here is 1, 1, 3 minus 4. Then I need to find the eigenvector. So check, first of all, here the matrix is going to be -1, 1, 1, -1. If you go back to the original one, it's A minus lambda in. We need to find the eigenvector, which is the x here. Let's say x1, x2. How equals 0. See, it's exactly the same thing here. This one here. Everything here, lambda, because we found the lambda, A minus lambda in times the x, which is the vector, equals 0. Here is that. I consider that x, which is x1, x2, which is the eigenvector. So how are we going to find the solution here? It's up to you. You want to convert it to 2 equations and solve it, or you want to say this is the matrix A minus lambda in with the 0 and find it going to be equal -1, 1, 1, -1, 0, 0. Because I'm using the matrix, I'm not going to convert that to a system and solve it. It's up to you. Both ways going to be right. Because our goal is to find the eigenvector. So if you want to solve it as a matrix, it's fine. If you want to convert these two as a system and find x1 and x2, it's fine also. Now I'm going to convert this one by using the raw echelon form. That means I need to convert this number to 0. So what I'm going to do, I'm just going to add R1 to R2. Okay? So what's going to happen here? Just add R1 because I need to convert this one to 0. This one's already is going to be 0. That means -1, 1, and here is 0. This one is going to be 0 because -1 plus 1 is going to be 0. 1 minus 1 also is going to be 0. And the last one is going to be 0. So from here, this is the x1, this is the x2. That means it's going to be -x1 plus x2 is going to be 0. And in this case, x1 is going to be equal x2. So the vector x, which is equal x1, x2, is going to be equal x1 equal x2. That means, can I say x2, x2? If you let x2 equal 1, that means it's equal 1, 1. This is the eigenvector, which is the same thing. Let's do it on another page. It's equal the same thing, the span of 1, 1. So you can write down the span. This is the same thing, the eigenvector. The span for 1, 1, which is the eigenspace. E, which is the eigenspace when lambda equal 4. This is only when lambda equal 4. We're going to plug in 2. So it's going to be 3 minus 2. Here is 1. And here is going to be 1 and 3 minus 2. That means the matrix is going to be 1, 1, 1, 1. So A minus lambda, which is equal to with in with the 0, that's we're going to find the eigenvector is going to be equal A, which is 1, 1, 1, 1. 2 zeros to find the eigenvector. The same thing, we need to convert this one by reduce row echelon form. Multiply this one by -1 and add it to the second row. So negative R1 plus R2. So it's going to be 1, 1, and here is the 0. This one is going to be 0, 0, and this one is 0. X1, X2, that means X1 is plus X2 is going to be equal 0. So X1 is going to be negative X2. So the eigenvector X is going to be, it's X1, X2. Then I can write it down X, negative X2 and X2. And that's mean if you choose 1, that means this one is going to be equal -1 and 1. Choose any number. I'm just choosing 1. So on the online assignment, you can choose any number. It's going to be right.
We can say that X2 be left with -1.
If you factor out the, yes, left over with 1 and left. That's right. So now, eigenspace when lambda equal 2 is going to be just going to write down as a span to the -1 and 1. And that's it. You see this example, they're going to ask you on the same time, find the eigenvalue and the eigenvector. It's going to be the long way. You have to find the eigenvalue and eigenvector, eigenspace on the same time, and you go back because you have 2 lambda, find the eigenvector for the second one and the eigenspace. And but we have only one formula. It says AX equal lambda X. Let's check that how we're going to use this formula. We have the A, we have the vector V. I'm going to say AV, not AX, because the vector they're telling you with the V. So this is the vector V. So AX equal lambda X, lambda V, AV equal lambda V, the same thing. The matrix A, which is -1, 1, 2, 0, times the vector V, 1, 2, equal lambda, which is, we don't have the lambda on this one, times the vector V, which is 1, 2. Now, how to prove that the vector V is the eigenvector of the matrix A with the certain lambda, okay? Because we don't have the eigenvalue. How to prove that? We have this formula. We have to prove that the lambda from the first equations is exactly the same lambda from the second one, okay? So what I'm going to do, I'm going to bring back the system. Let's check that. How to multiply these two matrices? The first row with this column and the second row with this column. So now, -1 times 1 is going to be -1, plus 1 times 2 is going to be 2, equal. How much is going to be here? Lambda times 1 is going to be lambda. Okay? Now let's check the second one. 2 times 1 is going to be 2. 0 times 2 is going to be plus 0, equal. lambda times 2 is going to be 2 lambda. That's mean. From the first one, lambda is going to be equal 1. From the second one, 2 lambda is going to be equal 2. That's mean lambda is going to be equal also 1. Check. From both these equations, we get exactly the same lambda. What's that mean? That means with this lambda, the vector 1, 2 is the eigenvector for this matrix A. So that's how we're going to prove it. Exactly the same formula we're going to use. Multiply this side, then equal it to the lambda with the vector. You have to get exactly the same lambda. That's how we're going to prove this is the eigenvector for the matrix A with lambda equal 1. Okay. We're going to show that V is the eigenvector, but I'm going to change the matrix. I'm going to do a matrix of 3 times 3, which is 0, 1, negative 1, 1, 1, 2, 1, 3, and 0. And V equal negative 3, 1, and let's choose 1 also. We need to prove that V is an eigenvector for A. Okay, so we're going to do exactly the same thing. We're going to say AX equal, or AV equal lambda V, because this is a vector. So here's the A, which is 0, 1, negative 1, 1, 1, 2, 1, 3, and 0, times with the vector negative 3, 1, and 1. We have to get, here's the lambda, and here is the vector, which is negative 3, 1, 1. Let's check that how we're going to do that. The first row times this column. Okay? So 0 times negative 3 is going to be 0. 1 times 1 plus 1. Negative 1 times 1 is going to be minus 1. Equal. Negative 3. And here is the lambda. The second row with this column. 1 times negative 3 is going to be negative 3. 1 times 1, so plus 1. 2 times 1, so plus 2. Equal 1 lambda. The third row with this column, 1 times negative 3 is going to be negative 3. 3 times 1 is going to be 3. 0 times 1 is going to be plus 0. Equal lambda. Check the lambda from these 3 equations. Equal what? From the first one, lambda equals 0. From the second one, lambda equals 0. From the third one, lambda equals 0. If you get one of these lambda not equal to the other, what are you going to say? You're going to say that, yeah, V is not the eigenvalue for this matrix. Okay? Vector corresponding to this eigenvalue. So, corresponding to this eigenvalue. The lambda. Now we have the matrix A, and we have the eigenvalue. We need to find the eigenvector. So always we're going to use this formula: A times the vector V equal lambda times the vector V. Okay, we're just going to plug in exactly the same thing. So the first thing I'm going to find, because we need to find the vector, I have the lambda. I'm going to say A minus the lambda with I. I need to find this part, okay? Then I'm going to find the eigenvector, which is the matrix A, 0, 3, negative 1, 4, minus lambda is 1, and I, it's 2 times 2 matrix, so I'm going to say 1, 0, 0, 1. That means this one is going to be 0 minus 1 is going to be negative 1. 3 minus 0 is going to be 3. Negative 1 minus 0 is going to be negative 1. And 4 minus 1 is going to be 3. Then we already know that A minus lambda with in with the vector, let's say v, which is x1, x2 is equal to 0. Everything here equal this matrix, which is negative 1, 3, negative 1, 3, times the vector, let's say x1, x2 equal 0. So now, again, it's up to you how you're going to find x1 and x2. Well, the easiest one is to reduce to row echelon form. So I'm going to say negative 1, 3, negative 1, 3, put 0, 0. I need to convert this number to 0, so I'm going to multiply by negative 1 and add it to 1. So R1 multiply by negative and add it to the R2. Negative 1 times negative 1 is going to be 1, plus negative 1 is going to be 0. Negative 1 times 3 is going to be negative 3, plus 3 also is going to be 0, and here is 0. The first row is going to be the same. That's mean negative x1 plus 3x2 is going to be 0. So x1 is going to be 3x2. If you want to make it easier, do not confuse yourself. Assume that x2 any variable, t, okay? We can say that let x2 equal t. So x1 is going to be 3t. That means the vector v is going to be x1, x2, which is equal, x1 is 3t, and x2 is going to be t. Let t equal 1. That means it's going to be the vector 3, 1. One of these vectors is going to be 3, 1. Can we say it's a span? The eigenspace when lambda equal 1 equal span to the vector 3, 1. That's it. This is if they ask you to find the eigenspace. You see, the eigenspace for when lambda equal 1 is going to be span 3 to the 1. Okay? That means the determinant only for this part to find the eigenvalue, which is going to be a minus lambda with in equals 0. So the determinant of a, which is 0, negative 1, negative 1, 0, minus 1, let's say lambda, I'm just going to distribute the lambda right away. So lambda 0, 0, lambda, everything equals 0. That means this one is going to be the determinant of the matrix 0 minus lambda, so it will be negative lambda here, -1 minus, here is -1, -1 minus 0, and also here -1, and here is going to be negative equals 0. How to find the determinant for 2 times 2 matrix? Just gonna multiply across. Negative lambda times negative lambda. I'm gonna write it down so you're not gonna forget. Minus -1 times -1 equals 0. That means it's going to be lambda squared minus 1 equals 0. So lambda is going to be plus or minus 1. Okay. So now we're going to go back. We finished from the first part. Now to find the eigenvector, which is then after that we can find the eigenspace. So when lambda equal 1, let's start with 1. We're going to plug in the 1. You don't have to go back to do these steps from the beginning. Just go ahead here. Remember, this is the important one. I'm going to plug in 1 here. So A is going to be -1. And here is -1. Here is -1. And here is going to be -1. Times the vector V equals 0. That's me. I'm going to say -1, -1, -1, -1. Times, let's say, x1, x2 equals 0. Then I'm going to write down as a system to reduce to echelon form. So give me -1, -1, -1, -1 with 2 zeros. Then how to reduce that? We're going to multiply R1 by negative sign and add it to R2. Yes or no? Then this one is going to be -1 times -1 plus this one is going to be 0. The same thing here is 0. This one is still 0. That's mean -1, -1, and 0. So -x1 minus x2 is going to be 0. So let's say x1 is going to be -x2. x1 is going to be -x2. Again, let x2 any variable. Let's say let x2 equal t. That means x1 equal -t. The vector v is going to be x1, x2, which is equal -t and t. If t equal 1, so it's going to be -1 and 1. So the eigenspace when lambda equal 1 is going to be equal the span of -1 and 1. So when lambda equal -1. Again, I'm going to go back here and now plug in -1 here. So be careful with the negative sign. So a -1 is going to be positive. That means the matrix is going to be 1, -1. And here is -1. Plug in -1 here is going to be -1 is going to be +1. So you see, it's exactly the same steps. Times the vector v is going to be 0. That means here is the system 1, -1, -1 and 1 times, let's say x1, x2, and this one equals 0. Convert this one to the system so we can solve it. 1, -1 and 0. -1, 1 and 0. Then what I'm going to do, I need to write down the matrix in row echelon form. So convert this one to 0. So I'm just going to say R1 plus R2. Here is the first row. The second one, this one is going to be 0. This one also is going to be 0, and this one 0. So x1 minus x2 is going to be equal equals 0. So x1 is going to be x2. Yes, it must be the same one. X1 is going to be equal to x2. Let x2 equal t. So x1 also equal t. Let's reflect over the line here. So it's going to be on the other side if we got it. So the let's see, the vector is going to be x1, x2, which is going to be t and t, the same one. Let t equal 1, so the same vector. That means the eigenspace for -1 is going to be the span of 1, 1. So reflect the first one. If we graph the first one, which is -1, 1. Let's do a simple graph here. -1 and 1. Here is the x and here is the y. You see the first vector is going to be like this. And the second vector is going to be 1, 1. So which type of reflection this one? Over the y-axis. So when I did these steps, I didn't confuse myself about what they says here, reflect in the line y equal -x. Because I have the matrix, I need to find the eigenvalue and go ahead find the eigenvector. Just go do the same steps. Check when you graph it. This is the first one, which is 1, 1, and this is the second one, which is -1. Okay. If they're telling you projection onto the x-axis, do not confuse yourself about what they're telling you. Go ahead, first of all, find the eigenvalue and eigenvector. When you graph it, you will see the projection. The first one and the second one. That means this line is going to be projected on this one. Okay? So don't confuse about what they're telling you. Clockwise, they're telling you counterclockwise 90 degrees. Do not confuse yourself. Find the eigenspace of the eigenvector for each one, because you're going to get 2 lambda, and you will see it's a clockwise 90 degree. Just prove that, okay?